So, what I would like to show you in this video is a special approach to complex numbers. Actually, you should have seen that theoretically, but I don't know and I'm not sure anymore if it is always taught when studying complex numbers. I mean, at school. Alright, recall the unit circle. Here we just have our coordinate system and we just have some angle alpha, whatever, also measured the arc length, and here this point at coordinates cosinus alpha, sinus alpha. Now recall the basic way to introduce complex numbers. We just introduce certain sums which are given in a way that this is a real number and this is a real number, so you have such sums, right? And you can do addition by such objects, right? Just formally defined such objects where in each component just the rules of calculating with real numbers work, right? And we have additional assumption like that. And rather than that, all the basic arithmetic laws work with these objects, right? That will be complex numbers. Right. In particular, we can multiply and just distributive law applies, and there you get certain calculation, right? You could do that. Right. Now you see, the thing is, when we have introduced such objects, and of course, nothing prevents us from just considering, instead of a y-axis, now another kind of a plane, where one of coordinates is kind of scaled by I. Right? It is all same numbers, but they are scaled by I. For example, here we have 1, but scaled by I. Here we have 2, but scaled by I. And in between, everything is scaled by I. Okay, but geometry stays the same. It's just some otherworldly object or otherworldly number which doesn't change the geometric relationships, right? So the geometry of the plane stays the same. Alright, if geometry stays the same, then of course these numbers can be just identified with two component vectors, right? So a plus bi could be drawn here. I don't know, here's some b, here's some a, here is a plus bi, right? Here in bi. And since geometry doesn't change, we could simply identify it. The point in the plane, right? Because it's kind of positioned exactly in the same point. If we just say that this only scales but doesn't change geometry, so in particular doesn't change lengths, so the number pi is exactly in the same position on this axis with exactly same distance as the number b on the y-axis, right? That would be kind of iy, right? So here, unit circle, that is I, and that is 1. Well, so you see, complex numbers can be naturally identified, and this is just, you don't have to think about it a lot, it's just a way to introduce this in our object and a way to think about it geometrically, very customary way. Just a plane is geometrically the same, but along this axis we want to have scaled by I, or number scaled by I. Alright, and then since geometry is the same, we can identify it with such a vector, right? Alright, but now recall this, right? If we now apply our I formalism to this thing here, what do we get? Well, here's one, here's our angle, and of course, here we just measure cosinus alpha as always. Here we measure sinus alpha, but don't forget this number is scaled by I, and this is just a number, you recall it's just coordinates. So those new abstract coordinates, so to speak, because I is a special object of some sort, are this. So you see, on the unit circle we have such complex numbers of this kind, right? Right. Now, well, I don't know if you already have seen it. Of course, you have seen convergence of sequences, right? Now, we could have a sequence S0, S1, S2, S3, and so on, right? A sequence. So those are real numbers. Essentially real numbers, and we just enumerate some real numbers within natural numbers, and the sequence might converge to something, or might not converge to something. So it might diverge, might not converge, or it might converge. Okay, so the sequence. Now we could consider a sequence like this, right? I mean, we could just define this new sequence in that way. This is all real numbers, so we could sum them up. And we could define this new sequence to be like E0, E1, right? We're just defining a new sequence. Nothing prevents us from doing that. Right. Now, it could turn out that this sequence converges. Very simple example. Our sequence is just constant 0. Example. Sn is equal to 0. Oh, I mean, you probably don't know this notation, so I will write for n element n. En converges, of course. Just converges to 0 because it's constantly 0. Right. Alright, and then it goes on. And this might converge. Right. Well, that's okay. And Mm, maybe I'll introduce that. And this is by the way I define it as. I define 0 is as 0. I define EY as 0 plus S1, and so on. So, I don't know if you are familiar with that notation. You see, this denotes a sum. So this is sum over Si. So that is, these are the terms in the sum, and this is from where I go and where I end. That is, if I know that this is terms in the sum, then I know there will be some S plus S, and here are the indices, different indices. And now I have to look from where do I go. So first I have to put a 0. This is just um, the place for the index I have now denoted it like that so that you see it clearly. Right, and I go to 0, so there's no other index. I just go from 0 to 0. There is one subterm, and that is, in this case, we just have that equal to S0. Okay, now the other situation, I just go from I equal to 0 over Si to 1. So I have to go from S0 first thing, and there could be some number of terms. Note from here what terms, and here I have I equals 0. Take this term, write it down. So then I increases by 1, and we are already done. We are already by 1, and we have S1. So in each step, when we have something like that, the index increases by 1. This is meant already. Right, this is of course so I go from 0 plus S1 plus S2. Right, increases by 1, and it has to go up to the upper bound. Right, and this. So this is just a shortcut, and this is the useful notation of this. Alright, but of course we could always write it out. No problem with that. Alright, now, of course you know this function, right? You know this function where we could take an x, and we just have e of x, so we could also denote it x of x. And this is the Euclidean number, right? This is just any element in R, and for any element in R, this gives some number, namely e to the power of this number. And Euclidean number is approximately something like 2714, and so on. Right. So, for example, p to the power of 2, or p to the power of 2, 1, 7, 7, 3, 4, or whatever. But how would we actually compute this? Well, you could use a calculator, but we are interested now in how to really compute this. And this is done as follows. You see the actual definition of that, because to compute that, you have to go back to the definition, but probably at school, if you didn't have some intensive courses going in depth, you never knew how to actually compute that. And we'd like to look at it more precisely. Alright, so what do we do for that? Well, you see, we consider this function, and now we'd like to consider its derivative, right? You know this notation, that's the derivative of x by x. And of course you know what it is. It is x, this e of x. And let's say we take derivative at point x0, right? We take this function, we compute its derivative at point x0, which is of course ex0, right? This is just the general notation for derivative, and this is derivative at this point. You might also have written that without this, just the derivative of that with respect to that, and you would say, well, the point is x. Doesn't matter. Just derivative of this function at the point x0 is exactly the value of a function at the point, right? And of course, that means that if we take derivative of derivative, and I'd like to take that at point x0, I'd like to take that at point x0. Don't be confused by that, just read first that thing here, right? We have our function. We have our function, and we take derivative at point x0, and then we take second derivative, that is derivative of this function that comes out of here, right? Sorry, of course, then I consider here a function. This is a whole function that is here. We just consider, let's see, well, I want to take one. So this is the first derivative, and this derivative, the derivative itself would be just same function, right? That would be just same function, but now for notation, we just have this derivative, and we take the derivative of the derivative, which is the function itself, as we know. And so we take the derivative of that into point x0, and so that is just x0, and that goes on like this. Alright. Now, you know, of course, that we do derivatives. And this is our exponential. This is 0. And this is, by the way, not a complex coordinate plane. This is just coordinate plane. Right? This is 1. And this is our exponential. Y equal to e of x. Right. And you know, of course, that if we take x0 and we take the derivative here, then what this indicates is just that this is the slope, right? This is the slope. That is, here we have alpha, and tangent alpha is equal to e x0, right? And of course, you also know that this shows the rate of change of the function in here. And if we get very close to this point, then this is exactly the rate of change, right? So this is this kind of approximates the function, right? So if we take this piece of the line to be very small, exactly around point ex0, sorry, it's 0, and that is just ex0, the function value, right? The function value is same as the slope. That is just two numbers, so it can be not. And here we just have this approximation, right? This thing approximates the function. What do we mean by that? Well, if we take this function, let's at this x0, right? And we get the very small dx from that away, right? This is dx, this is very small. That's the same as e x0, the value function in here, plus dx multiplied by x0 plus something very small, right? That is just the error, on the imprecision that we have. But if we are very small, this goes, of course, to zero, right? So what I have done here, look at that. We go from this place very little step, right? And then this line still approximates our function very well, right? Because in here it approximates it perfectly in the point itself. In the point itself, and around this point in a very little neighborhood. And you know why it approximates perfectly. How do we know that? Well, we actually know that this actually in this point, in this very point, it gives a rate of change of a function. And what is the rate of change of a function? This is how y changes with x. That is, in this very little neighborhood of a point, this function is kind of like this line, right? If this line shows a rate of change of the function in this point, a rate of change of y with respect to x, then that means that this function is kind of linear in the very small neighborhood of this point and linear exactly with the slope because it is a rate of change. So the function can be linearly approximated, right? And that is a very small neighborhood. What does it mean? Well, we go a little bit away from the point at which we are considering it, from the point x0, and we consider the value of this function, right? So something like here. And it is here, almost the line, but a little bit, no, but only really a little bit, and this bit goes to 0. So it is almost this. And how do we denote this? We just take the value on this tangent that corresponds to it, and this value will be given by, well, this tangent has this slope, and this tangent has this what is it called? This tangent has this this well, when we put here in that instead of that we put 0, and we considering this tangent, right? This is this describes a line because this is just a variable. You could also say that is some h, right? So you don't need to call it tx if it is confusing. It is just a variable h, right? And this is just a number, and then you realize that this is a line, right? This is describing a line, and this is our tangent. That is, this describes this line. And if we put h equal to 0, then we get e of x0, which means that this is, we could call x, we take any variable, we put it here, and we get this point, that is, at 3.0, we would have exactly this e of x0. Right. A little bit funny is how e of x0 would be negative. Right. Because I have not drawn it exactly. Of course, it will be like that, right? The slope would be certainly. Well, actually, no. Actually, no, because the slope would be certainly bigger than 1, right? And now I have put that to 0, which means that this is the intercept, right? Right, so we have moved that thing compared to how that, what that would look like. We have moved it away, but we should have moved it away by increasing the height, right? So that is a little bit funny. Right. That's okay. I have drawn it wrongly. That's true. The thing is, E is increasing, right? So Ex bigger than 0 for x bigger than 0. That is x bigger than 1, right? And this is the slope. And this has to go like this. But what I'm not getting is why that is that actually. Because that would mean that the slope is this is now a negative point, right? But this shouldn't be like that. But at some point it would be like that, no matter what you do. Right, that is funny. That is a little bit funny. We would have negative in here, even though plug in 0 would certainly give something positive. Right. This is certainly a tangent. Yes, I mean, this necessarily will give something negative here, right? But this is linear approximation, so that should give that. So what is going on? We have that as evaluation, that's right. And we have that, right? And we have same slope, right? Now we plug in that being 0, and we are at the point itself, right? But visually, it looks like this tangent will go like this, having intersection of the negative with the y-axis, right? So that is, if we put that to 0, right. That's actually weird. 1, 2, 3. Okay, that's 2, 7. And this 1, 2, 3. That's 2, 7. Okay. In 0 we have 1. In 1 we have 1, 2, 3, and 7, like this. In 2 we have approximately 7, 3. Okay, it's approximately 9 or something. 3, 4, 5, 6, 8, approximately something like that. Okay, that's the exponential, right? So, if we were here somewhere, then that certainly would intersect negative axis, right? Would intersect the axis negative. And the question is why that happens. Because obviously at x we would have something positive here. Right. we finish. We have dropped to the level of this constraint. But of course, if we would have some positive information, you would think, I mean, like that, you would think that this would be brought up like that, right? This would be brought up like that, right? And not put downwards. And of course, that's right. It would be brought up. So the question is, what is wrong here? Because this has to be this large value, right? It's zero. It's zero means here. Mm-hmm. Really, nothing seems to be wrong. It's exactly this. Ah, okay. Okay. Uh, this is where we position our attention, right? This is where Vy value of interest is given, and from this we just want to change Vy value in the way like the function changes, right? So in the way like the function changes means exactly that we go according to this tangent, right? In the way how the function changes to this point. And so very close to this point would have that change. Like going like that would change y like that, and would have this point, and there would be some difference from the function. But this difference would get very small uh, as we go closer and closer to the point at which we approximate, right? Right. So, so this is actually not the value of a tangent. That is wrong. But that is parallel to the tangent, right? We are only interested in the slope of a function. So we take this at this value and we go like that, right? So And if you wanted to compute the intercept of the actual tangent, and of course we would have to do something a little bit different. Namely, we would have to find with which intercept we actually get this at this point. That is our tangent entry point x0 is equal to ex0 plus yes, our tangent entry point x0 is equal to ex0. Right, and it has this slope. Right, so we have one point to which it goes, and we have a slope. Right. So if we have that, then we just have e0 plus h ex0. Actually, this is a 2-point x0, right? So we know that the 2-point x0 with tangent is x0. So we have to plug it in. And we get that this 2-point x0 with tangent itself is entry point x0, it is ex0, because this tangent goes through this point and this point, right? And so this is just x0 plus x0. x0 is exactly the value of that, and that is ex0, right? So, sorry, we simply have that point, and we don't know this this value, right? But now we know it because this is the tangent g of h is equal to plus h ex0, because we slope we simply have, right? And that means that a is equal 1 minus x0. So, and this indeed for x0 bigger than 1, that is negative in total, because that is positive, that is negative, so that a is negative, like here, right? So a very important thing, this is not the tangent itself, but the tangent only shows the slope, right? So the approximating thing is actually where we already take our slope from here, and we are only interested in the slope, and only slope enters as a relevant part, right? So this is parallel tangent, and then we put this tangent at this place, and we only take from it the slope. So this what participates here is not the tangent itself, right? It's just that we take this point, take this value of a function, and from here we go according to the tangent. That is, if we go by dx, we would have dx multiplied by the slope as usual, would go, we change this value at this point, x0, we change this value of the function by the law of the tangent, right? So, right, and very close to that, that would be same as the value of the function at this changed point x0 plus dx, and the function is now e, so e to the power of x0 plus dx. Right. Alright, now the confusion is cleared. And this is quite interesting, right? This kind of means that if we are very close, then that seems to be approximately x0 plus dx x0. And that is certainly a line, not our tangent, not the tangent that we have drawn here, but some line, right? A line. We took the point of a function and we continue by the line to get the value of the function by this inclination from the point, right? Now we call that we had that thing, right? The derivative of that, and that was x0. And you see, and now let's replace it to not be confused. Replace dx by h, because it doesn't matter. Dx is just a small piece of a line, so I mean of the horizontal line, just a piece on the x-axis, right? So we could denote it different. Doesn't matter. Only the structure meaning matters, right? Couple that. And what do we notice? Well, we notice that ddh of that, right? This is just a number. H is a variable because we can change it. We can go a little bit further from the point or a little bit closer to the point, right? Here's the point, x0, and on the axis, on the x-axis, we go closer to the point or further from the point. So this is our h. Right? We can now differentiate it by h, because that's a variable, so we differentiate by h. And this is independent of h. Just focus on variable h, okay? This is constant, and this gives the x0. That is what we find out. Alright, it doesn't matter where we differentiate, but I'm interested in particular in this derivative, so let's put it like that. Okay, we found out that we actually go inside, right? And of course we do, it is just that the slope of the line is the derivative, it is just how it works, right? So, of course. Alright. But now imagine I'm dissatisfied with my line approximation. It is just too rough. Too rough, I don't like this. Could I go further and approximate better? Well, you see this coincidence of derivative rates, and this approximates quite well in the neighborhood. So why don't we take this principle? We know, as you recall, okay, I don't have to write it out because you already know what is the first derivative of e, but just for explicitness, you know that this is again ex0, right? Now, why don't we find a function of a suitable type which has the second derivative also same as e at the point x0. That is, in this case, again, e x0. Well, you could wonder, what type of function should it be? Well, this was a line, right? And it's kind of nature to continue in the polynomial way. So what we'd like to have would be some h squared, and I don't know, something like some a, I don't know, some a as some constant, right? So something polynomial, right? What could it be? What should it be? Well, let's think. We want now to continue. Oops. The coincidence of derivatives here, we had by this approximation first derivative coinciding with our function, and like second derivative of our polynomial to coincide with our function. That is, what choice do we actually have? Let's see. Well, we'd like to have ex0 plus h, ex0 plus a h squared. And by polynomial, what is convenient, we only have to determine this coefficient, right? So that seems to be a good choice. We have started good with polynomials, and maybe we'll continue good. So let's take ddh, and again ddh, and we want it at the point x0. And don't be confused, we have variable h, but it doesn't matter what we call the variable. You could call it x now, you could leave here x. It only matters what the variable structurally means, right? And here we evaluate, of course, at x0 because we want this coincidence, and so we want ex0, so equal to the second derivative of our two approximate function. All right, what do we get? Well, we know what that is, just to differentiate by h, right? So, 2h, right? But now we have to differentiate another time, right? At x0 now. So differentiate by h. This is a constant, right? Doesn't depend on h. So I have just written this derivative out here. So this is, and now, after having written this derivative out, I have to differentiate this derivative and to evaluate what I get in general form at the point x0, right? And this derivative gives that. And now I differentiate that, and this is constant, and this is just a linear term, so that gives 2a. So evaluating at x0, no matter where I evaluate, is 2a. So this transforms in this, which gives a is equal to x0 divided by 2. Right, so then this polynomial, if we just put e x 0 plus h 0 plus e x 0 divided by 2 h squared has the following property. Let's call it something like, since it is the second degree, let's call it 2t2 of h is equal to polynomial, and t2 of h has properties. T2, the first derivative of h derivative of h, right, is equal x0 plus h x0. But you see, now we get this term, and this is kind of disturbing, right? We had that nice things that for the first approximation, the derivative coincided with the derivative of the first approximation. The derivative of the function coincided with the derivative of this linear approximation. We also call it the first approximation, and now it's destroyed. This is nice, but how could we alter this polynomial in a way so that both works? Well, you could so we still would have that, because that would be eliminated, right? So we would have ddh ht2 is equal exactly what we want, x0, which is equal to ddx 0. That is this derivative at x0. I just write it like that. From the context, it's clear what I mean, right? ddx dx x0. So this second derivative is indeed what we want, but this is not nice, right? We want to have first derivative still equal to the first derivative of the e function. And how do we alter this polynomial in a very self-suggestive way to get that? Well, it's simple. You see, this derivative which we want this derivative actually at x0, right? Because we want to approximate at x0, so we want the derivative at x0. So x0, right, and at x0, that would be just x0 x0, and here it didn't matter, but we took what derivative because h was eliminated, so we just take our get our x0, right? And now you see this is x0, and we should alter that somehow. And alter that in a self-suggestive way, so that we actually get eliminated when this is given, right? So this derivative should have this term eliminated, right? So we would like some ddh, we alter our t2 to t2 x0 is equal to 0. Right, so Now we want to alter it in some way to actually get 0, right? Right. So, that is of course, yes, that is what we like to have, and this should be eliminated in some way. Right. How do we get that? Well, you see, here we have that evaluation at x0, and it would be nice, and remember that this was h equal to x0, which was put in here because of this evaluation of this derivative, and when evaluation at x0, h transformed in this. But you see, this here, we actually have this evaluation where h is put to x0, right? So what if we replace h by h minus x0? Then, if we evaluated that at x0, then we surely would have here x0 minus x0, right? But wouldn't that destroy the other property? Let's see. Then the constant is eliminated. And here we have this variable multiplied by that minus this constant multiplied by that. That is eliminated. And that is eliminated as constant distributive law. This term is eliminated because it is constant. The average remains without h because h is cut out. Right? And now here, if we use the composition, the derivative of the composition, right? Then we get 2 in front, and we get derivative of that. And derivative of that, x0 is a constant, is eliminated, and here is 1. Right? So what we get is the product of this 1 multiplied by 2 and h minus x0. So we get, I'm just using this property of derivative of the composed function, and do not forget we consider that at the point x0, and so that is x0, and here we just get 1 from the inner derivative, right? But this plugged in x0 is 0, so that works. But does the second derivative work? Well, dh x0 dh to tilde is equal we already saw that from because of the first derivative here only that remained. So if we differentiate that, this eliminates, right? And here we just add this multiplied by 1, and now we have that, and we have to differentiate that, right? Because that was this derivative. Now not evaluated at x0, but general derivative here, and we have to differentiate the derivative. And what do we get? Well, of course, that anyway goes like that. And here again we have that. is a constant, and here h disappears, and here we have that. So both properties are satisfied. Wow, isn't that great? And what does it mean? Well, you see, now this thing is your approximation, right? Right. By the way, you might wonder what is with our linear approximation now? That is with this thing, because we had to approximate our a x plus h, which was the x earlier, right? We have to approximate it actually as a, I mean x0 plus h, which was the x earlier, right? x0 plus epsilon small, right? But now we have that. Now, that is just because we now always if we want to approximate our function now by this, then this is just approximately equal to something else. This is just e h tilde, so you could say that we put that equal to h tilde, and then that is equal to, so you see, one thing is like the structure, what means, and another thing is what properties it has. Right, so how we write something is not important. It is only important what structural role it has. Right, so I could just say that this is just this already includes this, right? So I could define this variable like this is x0, this is this h, and I just define this point itself to be h tilde, right? And then this gives you that. Right, but here it is just written like h, not h tilde, but you know, it is only structures that matter and not some concrete variables. Because it is the behavior that matters. Okay, so that means that this is now approximated by this line, which we see here. And pay attention, if we have dx here, according to that is h, right? H, no? And this x0 plus h is exactly h tilde. And from that it follows that h tilde minus x0 is exactly our h. So if we have such notation, then we definitely have that this corresponds to h, and then we have our approximation, right? And this corresponds to h. So this is this is a quadratic function, right? So this is linear term, this is quadratic term now. And what does it mean? Oh, this is just our line, just a line from here, right? Because this is h, right here. All right, this is our line. And what is our quadratic function doing there? Well, that's simple. The thing is, this quadratic function also approximates our thing with exactly those parameters, and it does it even better. But also pay attention, it is not just by the line the things that matter are the slope, and we put it on this point, and the parameters are now, well, the parameter by, you are more familiar probably with that, as quadratic function, so some parabola. Right now our C is not that, but more like this is our parabola, no? And it could be somehow shifted to something, but our A by x squared, or this now is quadratic value, is just that coefficient, right? Alright, this is h squared, this is x squared, this is our A, remember, only the form matters, and this is our B, right? So B would be already our slope of the line, and here's our coefficient, like the quadratic, the coefficient by the quadratic approximation, right? Alright, so this here would be some parabola which we would put exactly, so it is not necessarily 0. Here we have put it exactly, and then we go by our parabola from our point in one direction in the other direction, and it approximates our E function even better than the line, right? But now we could do this game more, right? So if it works that well, why not just take, well, in H2, this is like x0 plus h. When we are close to x0, that is h small, why not say, this is x0 plus h0 minus x0, x0 plus x0, h0 minus x0 squared plus x0 6 y6. Well, here we have like divided by 1. Here we have divided by 1 multiplied by 2. Here we have divided by 1 multiplied by 2 multiplied by 3. And we would claim that such, I don't know, maybe it goes until some n, right, could be. And this, of course, we factorial, right? and we call this, and of course it's approximately equal, right? So just like the line, there is some gap, but the approximation might become really good, right? Tn of children. Right, so we kind of bring it back. Remember, that's h. We bring it back to this point from here, and from this point we start to go by the line, by the slope. We go by the line, and then we go by more. We go by the quadratic function, but bring it back to this point, because this is where we start to go, and we go by this function, and then we bring it back to this point, and then we go by this function. This is all different approximation pictures, right? First we just consider only this, then we consider this, and so on. Right, and we claim, well, is then a dx n, I just denote like this, the nth derivative is equal to dgh, actually h tilde now, right? Because I want to distinguish it. x0 tn of h tilde. Yes, indeed. And that turns out to be true. This thing that we have defined here, and now you probably figure that they have defined it that like that for some reason. This thing turns out to have all the derivatives up to nth having the same as this funny polynomial. And we can see that even. Imagine we have n derivatives. Right? You have seen after the first derivative, this disappears, right? This disappears, and there remains h multiplied by, this is just h tilde, it's not a 2. There remains just h multiplied by, not even h, after the first derivative, this disappears completely, and from there remains a constant e to the power of x0, right? Because this disappears already after the first derivative, only that remains without h tilde, because we differentiated by h tilde, right? So only that constant remains. But now we go to a second derivative. Keep in mind that already disappears, only that constant remains. And by the second derivative, this disappears, right? And since by the second derivative, by the first derivative, we already had that became linear, right? And that only gave 1 in the composition derivative rule. So by the second derivative, already this h disappears because it became linear, right? And there remains only constant, right? And also this nicely is compatible with this 1 multiplied by 2. There remains 1. And after the second derivative, there remains only this constant, which is exactly the derivative at x0 of e, of the function e, right? Now, of course, here same e, and after third derivative, of course, that disappears. But now consider what happens by the third derivative here. And of course, also pay attention after the first derivative that remains only constant here. But what happens here when we just plug in x0? Well, here the term is linear, so here we have h tilde minus x0 as one of the terms, as one of the multiplicative terms, right? And we plug in x0 is 0. Here, of course, same, because this power is only reduced by 1 after first derivative. Here same, here same, here same. So those all became 0. And total, we have after first derivative had exactly the derivative at point x0 of e. The first derivative comes out of e at the point x0, right? And we go to the second, and you can see here again the powers are reduced only by 2. So at least the linear term remains. Then we plug in x0, everything here disappears, and here remains this constant where exactly the right way this 2 eliminates with this 2, and then only this derivative after plugging x0. Oh, actually here only this remains, and plugging x0 just eliminates those terms, right? And this has been written after third derivative, same game that after first derivative eliminates with that, there remains a 2, then a 2 goes to there, then we have 1 at the corresponding point, and after the third derivative indeed turns out that what happens is again linear term is left alone and is differentiated, and only this constant remains, and everything here in the higher terms disappears. If you wanted, you could prove that this works by induction. I will do that. It's a boring proof. You just have to formalize the steps that I have just narrated. Right. And indeed, the approximation becomes even better. So our guess that having more and more derivative coincide with our function will give you an even better approximation, ever better approximation, is true. It is true. Oh, wow. Well, now that's great. That's just great. That is, if we go to higher polynomials, that is to the third power and so on, again, pay attention that we position that at that point and we go in how the graph tells us, but it is not necessarily having the intercept in the right way. Right? And it approximates even better. And it turns out that if you plot it, then from the 100th degree or even from 20 something degree, it already approximates perfectly. You can see the difference. Of course, not perfectly, but you can see the difference visually. Right. Right. That is great. Now consider a particular point, because actually we have now found a way to compute this, right? If we take x0 like that, and we take h like that, then what we get is computation of e, which is not only approximate, but, well, looks good. Alright. But now, by the way, so that we have it consistent with what we had, otherwise we just write that dx0. This is just a formal thing, right? But we'd like to have it to 0 x0 multiplied by 0 factorial, and it's just definition, but you know it, right? Right. And you see here, in this case, we all coincide, but actually what we did was plug in dx at x0 of x here, dx second derivative at x0 of x, and so on. Here we plugged in third derivative at x0 and so on. Here, customarily, we just call this zeroth derivative. Zeroth derivative is kind of function itself at x0. Right. So, but why did I introduce that? Those funny polynomials and something. By the way, these funny polynomials are called Taylor polynomials. And this is the way to approximate functions by polynomials. Right. So it does not only work by e function, it works by all functions that are differentiable, let's say, n times, then it works till the end, maybe n plus 1 times, then it works till the end. I don't remember exactly. I would have to look it up. I mean, the differentiability works, of course, but if it also is nice, what comes out is not the question. But okay. Okay, so why did I like to show you that actually? Well, you see what the thing is. The thing is, if we take x0 equal to 0, then for very small values of h, we have a decent approximation here around 0, right? Alright. But now, so that would be just e to the power of small h, we would approximate it like that. Right? Right. All right. Then we'd like to extend this approximation to larger values of h, right? How do we do that? Well, you see, plugging in 0, we just have that those things will all become 1, right? And you will just have here h to the power of something and so on. Right. But this only works for small h's. Right. So how do we extend it to larger h? Well, um, well, how would I do that? Hmm. Well, if I had to do that, you see, by the properties of e function, you actually have this identity, right? So if x0 is equal to 0, then you just have that this is e to the power of h. But if h is large, then it doesn't use much. just observe what we have done here, right? We have that this is approximately equal to this. Okay, now I know how. Um, no, I don't necessarily know, actually. If we have a large H, then it doesn't look like that. Okay. But now consider this approximation in a little bit different setting. You see, this, if you recall, the sums of sequences. If we are given an x0 and we are given an h2, right? And that could be seen as a sequence, right? This is just real numbers, right? By given x h2 and x0, so no problem with that. This is now a sequence, and this continues on and on, right? And now this is a sequence too, right? Just like we had those summations. Alright, of course commutativity, but let me stay consistent. I could have written that after that because of commutativity, but let me stay consistent. Okay, and that goes on and on. Right. Now, what is that? Just recall what we had, right? Now, the dependence on I is a little bit more complicated, right? But there's no problem with that. Just write it out like it's supposed to be. And that's it. If you write it out, you see you go from I equals 0 to 0. That is, you have only one term where I is plugged in equal to 0. And when you compute that and you get 0, 0 factorial, you have 0, you have 0 here. So you have 1 here, and then you get that. So, same thing here, right? And go to here, and go to here, go to here, go to here, go to here, go until 1, right? You see that. Just have some terms go from 0 to 1, plug in 0, then increase I by 1, and have n, and we have just I equals 0 and x0, so that is 0, and plug consider this subjob for 0, and you increase I by 1, you to get I equal to 1, then you get here 1 factorial, here you get 1, this is the second subjob, then you get I equal 2, you plug it in, you get that subjob, and so on. Right. Then it turns out that with some sequence, that is the sequence of the sums, right? Sequence of those sums converges. That is, we increase that index more, that indeed converges, right? All right. And it does so to so exactly what we wanted to approximate. If we go, so to speak, to infinity, then we get the exact result. And how that is done, well, that you can see in higher mathematics. If someone is a little bit knowledgeable, well, it's quotient criterion here for convergence of some series. I think I would use quotient criterion, yeah. So then it's not hard to mention. Oh, well, no, that's actually easier. Plug in here. And here, get h. And this is not for small h anymore, because our approximation becomes that good that it approximates everywhere. Get for h inventor a 0 h is equal I equals 0, and that's that limit of those sums, that is, we write that 1 plus 1 plus 2 blah blah blah, and this sequence converges to something, right? So this limit we write like that, like we summed infinitely many terms, but of course that is not meant, but we meant the limit of a sum sequence is meant. And this is very known formula. You may be heard of, maybe not. Since went to perfect approximation. Or you see, by going to perfect approximation, it doesn't matter anymore what distance h is from, because our approximation like reaches everywhere. Approximacy function perfectly. So there wouldn't be much meaning in saying, well, it only works for such small range, because well, the further we go, the better approximation gets. The better the approximation gets, and then it would be just impossible to say, well, it just goes until there, that range, because we actually go infinitely far in the improving the approximation. And this is what I wanted to get now. Now this I is a little bit bad. Of course, J works just the same. It's just the name of the index, right? Now remember that we can compute things by complex numbers just the same, right? You remember we are arithmetically doing all the same things, only that there is this weird I being square root of -1, or better to say, having the second power equal to -1. Of course, this is possible because we just can multiply IR multiplied by R, and now pay attention, I is not index, that is I in the complex numbers, so that is the imaginary unit, right? So we can do the sums all the same, and we can consider, well, maybe even that converges, right? Right. Turns out that it does indeed converge, and it is very easily shown when you know the corresponding tools. It's basically uh, same as convergence of this here, but now I won't go into it. Turns out it doesn't indeed converge, and furthermore, one gets EIR, we just write it the same, right? And now it is not taken to the power in any sensible sense, but it is simply defined as in any automatically sensible sense. This is more sensible. One gets and what does that mean? Well, of course, it doesn't mean something like, oh, something very funny or something like this. No. It's not that. It's just this could turn out to be a complex number. I mean, truly complex number, right? Could be because we take here some kind of convergence, so here comes some number that is in general complex, right? Right. And now this is its real part, this is its imaginary part. Right. But what does it mean that this is equal to this kind of exponential equal to some? Well, this is very simple. You see, recall cosinus. Cosinus zeroth derivative, right? This is not to the power, this is derivative. Let's denote it like that. Cosinus to I mean that's the first derivative. S equal minus sinus cosinus second derivative is correspondingly minus cosinus third derivative is sinus cosinus fourth derivative is cosinus, I'm sorry, cosine, right? And sinus zeroth derivative sinus first derivative is cosinus. Then we can just continue here. Sinus second derivative is minus sinus third derivative is minus cosinus sinus fourth derivative is sinus. Right, and so it goes. Right. And now just the same as here, we consider the Taylor polynomials. As I told you, those funny T polynomials are called Taylor polynomials actually. Okay, so but let's do it first, right? Because we already have something with it. So cosinus is equal to what? If we just consider that, and that also we say again to converge, but the question is what exactly do we have? Well, let's look at this. We consider cosinus at 0, of course, and we consider some small h, and we consider then, well, cosinus at 0 itself is just cosinus at 0, that is cosinus at 0 is just 1. We call the circle, right? Now we have Cosinus is minus sinus, right? Minus sinus at 0 is just 0. So we just have that this is 0. This was for h to the power 1, right? We just take this and we just take away this point at which we consider that, but this point is now 0, so nothing is taken away. So now minus cosinus at 0 is just minus 1, which means minus 1, and we have minus 1/2, and we have like h squared, right? Alright. So now we have something like, again probably plus, yes, plus, but this is again sinus at 0, so that is 0. Short. Right. So we have here 1 divided by 6. Here we have 4, and here it begins to repeat. Here we have just h4. Right. So we can probably see the pattern. Of course, it will repeat also in minuses and pluses, right? Ah, okay, that's wrong. Of course, that. So we see something like right. Looks pretty much like it. But we should be careful. This would not work, because if we would just put that, and of course we couldn't have here minus it. So you might think that we would have to put -1. But that would also not work, because that would be 2. Right? So, and here again, you see here h4, and here it goes again. It goes again with minus sinus. So by 5 it's nothing, but by 6 it is actually -1. So here you have kind of 2k plus 1. Right, so by 0. But this again would not work, because by 0 you didn't have -1, right? But by 0 you should not have anything. So let's try this. So now it seems to work. Right, so what we put here seems to be something like that. This is by the way how your calculator in truth the um, computes the exponential function, and cosinus and sinus. It just takes a good enough approximation via such things. Maybe it use another series, but well, this would do. Like for 20 terms, it's already very decent. Okay, I believe that would be cosinus. Maybe it's a little bit something different, or you can think about what sinus is. And again, we take infinitely many terms, so the approximation becomes perfect, and so we can represent cosinus like this. But of course, the calculator can't just compute it completely. Alright. And human also can't. Except for very simple values. Alright, and then it turns out, if you consider those representations in infinite subseries, that this is true. That is Euclidean identity. So, and this, you recognize this, right? This is exactly the coordinates of point corresponding to an angle in the complex plane. Only that angle is now called R. Doesn't matter, right? But now it turns out, as we said first, we can identify this with that, as we said. Right? Because it's just some abstract object, and then we just think of this unit like this, and geometrically it's the same, so we can identify. Right. Alright. This is same as but this is same as that is those points on the circle are actually all those points actually evaluations of this function. And wow, anything, because alpha element r, and we just go, if we achieve 2 pi in the angle, we just continue to go, and geometrically we are at the same point. So that is same as cosinus alpha plus, I don't know, 100 pi, wait, yes, 100 pi and 1000 pi, whatever else. That's all same thing, geometrically, right? So the complex number is the same. So that is for any alpha element R. Those things are bound to repeat. Those numbers now, those numbers, not just cosinus, sinus, but now we have a connection to complex exponential, bound to repeat, and are all this nice circle. Remember, that's unit circle. That's where we had cosinus, sinus as coordinates, and now also cosinus is I sinus as complex coordinates. Fingers. That is great, right? Now you see that radius is 1, right? We know that to be 1, we have taken unit circle. And of course, since we identify those points like that, it's pretty natural. Since we identify them geometrically, pretty natural to say, well, those points we define for them just in the same way for those points. We define for them some kind of distance from the origin, right? So if you have something like that, or you also recall this identification. This is very distant, could take this. Just define for that, and we could of course also say plus b define the c squared plus b squared, and that is why that is because that is same point, and for that we already know how the distance works. The distance for that works just well AB, and this is origin 0, 0, and we want this distance. So we just have to, well, in this case, if I drawn it like that, could have drawn it like that, right? So we just have, but it doesn't matter what we order is, just this distance, plus this distance, and we compute this hypotenuse, right? So it's exactly a squared plus b squared. And since we said we multiplication by imaginary union doesn't change geometry, we keep that and have that distance, right? So So the geometrical distance of this number is actually 1, because that is 1. So if we want to place the complex numbers geometrically in the plane, we just do this. We place them exactly at those points and identify them with those points. Right. Now, what is next? Well, next, finally, consider all complex numbers. Well, we just said that we identify the complex numbers with the points in the plane, right? And we just said that these complex numbers kinda have distance 1. By which we just mean that they are imaginary part and u part just gives 1, just by definition of cosinus and sinus. Here, nothing changes in that regard. This definition still applies. It's just cosinus and sinus as usual, and that now there is this imaginary unit. Taking imaginary u part means work with real numbers anyway. So, and this, thanks to geometrical identification, identified with this number, right? With this point. Right. We call this absolute value of a complex numbers, more generally. This. Right. Right. And now you just have those numbers established as EI, it's called 5. And they all are somewhere in the circle. And those are exactly the numbers on the circle. So on the spiral, more exactly. You remember the spiral, right? So the numbers e to the power of I multiplied by some real number exactly all the complex numbers on the spiral. Right. Because as I said, that could go round and round, but since we identified geometrically, it would be all same points that it goes through. Right. So now, of course, this is a number, right? So we could multiply it by r. But what would happen with that geometrically? So we know that this is that. And remember all possible identifications. Maybe I'm going to have that now. This is 5. R sinus I. And just look at what point that corresponds now geometrically. Same D, right? I don't know what point it corresponds now to, so I skip that step by corresponding first to the point of imaginary coordinate. Just want to have geometric correspondence, right? So, and with that it follows that this number is a complex number, right? Everything is fine. That thing which we call the absolute value of that squared plus that squared. I have already solved that squared here. So that is actually, of course, R is, I don't need to, that's just a real number. R is a real number. Right. No, actually, we just don't need it. We just don't need it. You'll see the second one. We can say that this is equal 0. Bigger or equal 0. There's no problem with that. Okay, again. Okay. And that is just that, and you know that this is bigger or equal 0. So this is 1, and this is just R. What does that actually mean? Well, remember the geometric distance, which is geometric distance at that point, right? From the origin is R, which just means the distance of this point from the origin is R. And that means any such point is actually on the circle with radius R. And now, of course, we could have gone, I don't know, that could be R phi 2 and so on. And so we can have those two parameters, R and phi. And when we take any complex number that we could imagine, like take any A, B element R and take an A plus Pi, right? Then we do the following. It doesn't change the number, you'll see in a second what I mean. These are just computations of real numbers, right? So nothing changes. Right, nothing changes at all. But this is now, of course, since A is subset of R small or equal P plus B squared, we have same with B, of course, B. So that's the same. And if that is the case, well, we know that this actually works because our cosinus is defined everywhere there, right? So just take a cosinus of that, and this is an angle, right? So let's call it now. Here we have to be careful because we don't know where our angle is. So depending on how the number is positioned, we would get different things to take as a cosinus because it like to, you remember that a cosinus would always give us an angle in here, right? We have discussed it earlier. A cosinus would always give us an angle here, but it might be a cosine. Cosine would always give us an angle here, but it might be not a suitable fit. And so to have a suitable angle, meaning that where our number actually is positioned, in the sense that this here places our number on a circle, and we claim that it is circle with its radius. But for that, we would have to show that this point is actually the coordinates of cosine phi, sinus phi, so that this would be multiple of radius of unit circles, but this point would be unit circle, right? And then we just say we just say our cosine is equal to, if we would just say that is equal to our angle, we're going to show that this is always on some circle, right? So, but if you would have claimed that this is equal to our angle, it wouldn't be quite right. Instead, we would have to distinguish. You see, the distinguishment is simple. Distinction is simple. We just have to look where our number is, right? So depending on the signs of A and B, we have that if A is positive and B is positive, then of course A bigger 0, bigger 0, B bigger 0, and of course this is 0. Now here of course A is small equals 0 and B is 0. I see that here. Here that is negative. Right. So here both negative. And here this is negative. And this is positive. Right. This is the and we see that we have a division into 4 quadrants, right? And here same. Just look first. Oh, what of the 4 cases it is? If it is this case or this case, we are fine, right? If those are two other cases, not necessary. So let's not call it a cos, but a cos C plus a cos. And C could be something. So for example, if we turn out to be here both negative, then on our circle we would be somewhere here on our big circle. Right, here would be a region somewhere, and that would be a circle. something like that, right? Big circle. And we would have that. And then we would have, if that is some point, right? Don't click here, which we have gotten the right angle with our questions. With our cosines, well, that's simple. You see, if that is the same angle we would get simply for reversing that, because we would just have that, right? So we would just have gotten same angle. Because three cosines with cosines is the same actually for here. And but it is not the simple here. Right, so what we would have gotten would be actually the arccosines of that thing, right? So what we would have to adjust to get it properly. Or we could just take cosines of something else. You see, if we are in here, we could just take same absolute value, but could revert our p. So revert with sine of p, meaning we take minus p instead, and taking minus p, we could revert both sides, which would give us for that the arccosines of that. And so we would revert this sign to a positive one, right? And we would revert beta, b to a positive one, right? But the interesting part is the arccosines would be seen by reversing that and reversing that, or simply reversing that. Of course, it will be the same because reversing beta wouldn't change anything, right? But reversing k would change something. And we revert a and compute the arccosines of same stuff. Right? So that will be same for beta, right? And we will compute the arccosines and the arccosine, and that would be exactly that angle. But now we have to go back. So what we have computed, the angle of my arccosine was this point where we had b a like that, and have now reverted minus b minus a. Okay, and that of course gives you the arccosine of that angle, which is rotated exactly by pi, right? By 180 degrees, and then you have to add pi. So in that case, for example, c would be equal pi, for example, right? All right, engineer did that, and that would be our angle phi. And so Of course, just by definition, that cosine phi would be equal to take such a angle that is suitable for our position and simultaneously satisfies this. Right. And then, of course, we can already see that this thing is um, if you square this, you get that, and so you see that 1 minus cosine phi is equal exactly to b squared, and that is equal to sinus. Oh, sorry, I mean that, right? Which is equal b squared plus b squared, right? And that means that that this is equal to sinus if we take the square, right? This is important thing. And of course, it is not necessarily that we take the square root, so it might be some plus minus business, so you don't know for sure, right? Yeah, it's just like here, right? Here also could be some plus minus 1, some cosine phi plus some cosine c, and so that could be something like that. We would have considered the situation, right? But in total, it is just that, right? All right, and then that gives indeed the important thing is for some phi, it gives us and here, which means that this number, arbitrary complex number, is indeed that circle with that radius. And with a projection the unit circle. So all with the coordinates of unit circle on this number is being exactly cosine phi plus I sinus phi. And of course, if you have some cosine phi, I sinus phi here, and multiply by r, you just catapult it to the circle with your radius r, which we have seen here. Right? Just catapult this circle with your radius r. Right? But this is an important thing. Then in any complex number lies on a circle with radius and test distance corresponding point AB to the origin. And pay attention, I have skipped this step A plus IB. It's obvious by now, right? And has angle on the circle equal to phi, and it's I phi, and it's R AI phi representation. And that is of course that. And so we know that this representation exists exactly because of that, because we know what that is. That is just by Euclidean identity, right? That is that. So this representation truly, necessarily exists. Right, that is, if we take our plane and we said geometrically the complex numbers can be identified with points in this plane, then what we have, this is the complex number 0, and we have circles and radius, and this radius is really approximately 0, so it's with a small circle around this, and then here, these things are complex numbers, right? They are just circles. Geometrically, they are circles in the plane. We are identified with corresponding points. They are circles in the plane which cover the whole plane and which are indeed shown. This is radius 0, this is radius absolutely small epsilon, this is larger radius, this is larger radius, and so on. So the totality of all complex numbers amounts to simply having that unit circle having numbers like cosinus phi, alpha sinus phi, right? This is the initial point, and this is of course I phi, right? And now in both directions we just go and extend our circle, so and this is done by some tilde, and this is done by some r hat. So this is some r hat multiplied by phi, and this is some Matilda multiplied by 5. So this is complex numbers. There's nothing else in it, just that. This is really beautiful, stunningly beautiful, isn't it? It means the complex numbers are really reduced via the geometrical identification to something particularly simple. It's just any complex number a plus ib is nothing else but for some phi plus some unique parameter and some. If you want it to be unique, then we just have to restrict that angle because otherwise it could go in a spiral. The spiral it would always be the same angle we add to pi, right? So if we want it to be unique, then we just restrict it to this. Like this is complex numbers, just circles that cover plane disjunct circles. So complex numbers of different radii where radii come from geometrical identification. Right. Well, with that I'd like to finish for now. I didn't consider the necessity to do actually the Taylor approximation to introduce this, but then I understood that it is necessary, and hence it has become a little lengthy. But okay, see you next time.